Yeah, we can.
Okay, so we can start, right? So hello everyone. So today we are going to see about propulsion questions from GATE 2026 aerospace paper. So in this year paper, so the general review is like many questions were asked from propulsion. It was due from many years. So this time they distributed major portion of marks to propulsion too. And as we can see here, there were total 16 questions. So out of which like 10 questions were coming from 2 mark section. So it was interesting. And this time also they tested most of the fundamentals rather than direct formula based questions. So it is definitely an interesting paper to see. Let's go ahead. So the first question we have here is a more generic question, not just the propulsion related. A following equation with respect to say like phi, it's a function of x and t, where a is non-zero constant represents. So there were 4 options: linear wave propagation, transient heat conduction, Newton's law of cooling, radiative transfer. Okay, so this is a very straightforward question if you know the equation. So this is sometimes referred to as one-dimensional wave propagation, unidirectional wave propagation, I would say. So this is actually option A, and we know the heat conduction is related to second order of this derivative, whereas Newton's law of cooling, that is straightforward, that tells you temperature is proportional to the the heat is proportional to the uh, changes in temperature. So then radiative heat transfer, that has a different equation, right? So this is uh, wave equation. So and the solution to this one will be like function of say like if it is x, yeah, so x minus at form, where a is characterized by a characteristic speed, it's a constant, and the information has to propagate along this called characteristic lines. So this is a famous D'Alembert solution. Okay, so I think, yeah, so correct option is A. So our next question is, which one of the following makes an ideal air standard Stirling cycle, right? So this is again, the Stirling cycle is not that usual that we see in air breathing propulsion or like land-based propulsion systems. So, but what is Stirling cycle is? So it involves 2 isothermal compression and isothermal compression and expansion processes, and 2 constant volume heat addition and heat rejection system. So, so this one with the given options, we have 2 reversible isobars and 2 reversible adiabatics. So this is not correct. 2 reversible isotherms and 2 reversible isobars. This is also not correct. And 2 reversible isotherms and 2 reversible isocores. Yeah, so this is one, right? So 2 reversible isotherms and 2 reversible constant volume process. So this is what Stirling cycle means. An ideal Stirling cycle, right? Okay. So then, yeah. So this part of the propulsion that we discuss every time when we start our propulsion sections. So starting with ideal cycles, but we hardly see any questions coming from an ideal cycle. So this time they did include one question from ideal cycle, and it's very fundamental too, and it's very interesting question. So what we have here is, in the figure below depicts two ideal gas turbine cycles, cycle 1, 2, 3, 4, 1. So that is 1, 2, 3, 4, and 1. That is one cycle. The other cycle is 1, 2, 3 dash, 4 dash, and 1. Right? So which one of the following statement is false? So statements is false. So that's what they are asking. So let's before even moving on to the options that we have, let's just see like what are the things that we have from given TS diagram, right? So we have, say like this is P1 is equal to constant line, this is P2 is equal to constant line. So we are operating between same pressure ratios, right, in both the cycles. So that means, so let me call R is equal to P2 by P1, that is constant for both the cycles. So what else we have here? So since it is for a given gas, so I can also treat gamma to be constant for both the process. So that means what is my work output? That is going to be the temperature differences. So in other words, the enthalpy differences. So since it's an ideal cycle, we treat Cp to be constant. So the enthalpy differences between the turbine work and a compressor work, right? So that means work net depends on the temperature difference. So for the work net for the 1, 2, 3, 4 cycle, that is going to be T3 minus T4 minus T2 minus T1 in this way. So Cp is multiplied, so I will just take Cp constant. Okay, so for the cycle 2, we will have T3 dash minus T4 minus T2 minus T1. So now if you see here, so T3 dash is higher than T3. So that means this difference is higher than this difference. So that means the net work output is increased from 1, 2, 3, 4 cycle to 1, 2, 3 dash 4 dash 1 cycle. So it does depend on maximum cycle temperature. Whereas if I look at the efficiency that we have derived in our classes, so that for a simple Brayton cycle, that turns out to be 1 minus 1 over R to the power of gamma minus 1 by gamma. So that means it just depends on the pressure ratio and the type of the gas that we are using. So since we are operating under the same pressure ratio, so that means it is independent of cycle maximum temperature. So that means for the given two cycle configurations, so we have same thermal efficiency. So it is not going to change. So now look at the options that we have. So the thermal efficiency of the two cycle is the same. So that is correct. The specific work of the two cycles is the same. So that is not correct because we have seen the temperature increases, cycle maximum temperature increases. So that means the specific work output also increases. Then the process 2 to 3 and 2 to 3 dash are isobaric. Yes, we are dealing with the constant pressure heat addition. So that's correct. The amount of heat added in the combustion process is greater for cycle 1, 2, 3 dash 4 dash 1, right? Because we are increasing from 2 to 3 dash as opposed to 2 to 3. So we have to add more energy to get the higher cycle maximum temperature. So that means, so this statement is also correct. So only statement that is false from the given statements is statement B. So let's see about the official answer. So that says, yes, it is option B. Okay. So moving on to the next question. Here we have, for a given air standard power, the propulsive efficiency of a turbofan engine is more than that of turbojet engine. So which of the following is or are the reason or reasons for this? So this is an interesting question. So we have a propulsive power that is usually defined as what? Thrust power to that of engine output power, right? So the engine output power depends on the kinetic energy of the system that we are dealing with. So that does depend on higher, um, the difference in the jet exhaust speed to that of the incoming speed. So it is proportional to that. Whereas a thrust power is going to be the thrust times the forward speed, CI. And thrust for a turbojet engine depends on mass flow rate and the exhaust speed, directly proportional. Whereas thrust for the, this is for say jet, and thrust for the turbofan engines depends on mass flow rate and CJ, as well as the fan thrust, so or the cold thrust. So in that case, so it depends on both mass flow rate and the exhaust velocity of the engine as well as exhaust velocity of the fan. So engine, I mean the core stream. So it means if I increase the thrust power or if I decrease the kinetic energy differences, so I can increase the propulsive efficiency. So that means one of these two conditions or both of these conditions can increase the propulsive efficiency. So now look at the given options. So the mass flow rate is more for turbofan engine, right? So we are including a fan, so we are allowing more mass to flow into the engine, the overall engine. So that means this is responsible for increasing propulsive efficiency. So we can see if I increase the mass flow rate, the thrust power increases. And the exit velocity is lower for turbofan engine. Yes, this can cause increase in propulsive efficiency because it directly relates the engine output power that we have in propulsive efficiency, efficiency definition. So that means this is true. Whereas turbofan engine operates at lower altitude. So for as far as the efficiency, propulsive efficiency is concerned, the altitude is not a direct variable that comes into picture, because like we are insufficiently provided some of these data to quantify whether the effect of altitude is going to increase or decrease the efficiency. The same goes for power, because we don't have an exact number for engine output power to say like how much of those power is utilized in running a fan or some and producing the thrust. So in that sense, so these two options that we have, option C and D, so they are not directly relevant to the propulsive efficiency of these two engines to correlate between them. So I am not going to choose these two options if it is given to me. So whereas A and B, for certainly they are correct reasons for why the propulsive efficiency in turbofan is more, right? So this needs more of a argument from your end to decide which of these two, which of these options are actually correct. So yeah, so correct options they're given in the key is also A and B. Okay, so let's move on to the next question. Okay, yeah. So this one again, very interesting question. The figure below shows the blading of the rotors of two different axial turbo machines under their typical operating conditions, labeled as configuration 1 and configuration 2. Which of the following statement or statements is or are true? Again, it's a multiple selection kind of question. What do we have here? So see, this one, the blades are facing downward, right? Like this is my suction side, this is my pressure side of an aerofoil. So that means, so now we have to decide based on the configuration. So the flow is coming in this direction, axial flow. And we have flow that is leaving axially, absolute flow. And how the velocity from this end is going to be the relative to the blade. That is my, say like W, the relative speed at the exit, and relative speed at the entrance, that is W1, right? So now you see both of these speeds, the relative to the blade, are in the same direction. So what configuration gives you the relative velocity vectors to be on the same direction? So that means it is compressor, right? So similarly, if you look at this condition, say flow is coming in this direction, blade is receiving a fluid in this direction, whereas relative to the blade, whereas the relative velocity leaving the blade is in this direction. So there is a directional change for the velocity vector. So that means this must corresponds to turbine. Right? So now, if this is the configuration for turbine, so then in which direction the turbine blade should move? Because if there is a flow that is going in this direction, so there is a reaction force that will apply on the opposite direction. So that makes this blade to move in this direction. So in the given configuration, plus theta corresponding to this direction. So the blades are rotating in this direction. So now look at our configuration 1. So that is for compressor. So velocity vector is in, the relative velocity vector is in this direction. CA is in this direction. That means, so our velocity vector relation says C is equal to U plus W. So to balance that one, so absolute velocity should be vector sum of these two velocity vectors. So that means C has to be in this direction, right? So that means U, W plus U, so that will be in this direction. So this blade is rotating in this direction. So that is opposite to the given theta direction, right? So now look at the options. Configuration 1 corresponds to the rotor of a compressor and configuration 2 corresponding to the rotor of a turbine. So this we established, so this is true. So if this is true, this cannot be true. They're just exactly opposite statements. So then the rotor blades of the turbo machine in configuration 1 move along plus theta direction. That we have seen for the given condition, it is moving opposite to that given direction. So that means it is not true. So the other option says the rotor blades of the turbo machine in configuration 2 move along the plus theta direction. That is true because we have seen the reaction force will make that blade to move in the direction that is given in the figure. So in this question, statement A and statement A and statement D are true. So if you look at the answers, so yes, the correct statements are A and D. Okay. Then, okay, again we have a question from compressor. So here it is showing a multi-stage axial compressor can operate at 2 points A and B, both of which lie on the same speed line. So as shown in the figure below. If eta is isentropic efficiency of the compressor, select the statement that is true. Right? So now look at this map. So it is map between the pressure ratio as a function of mass flow rate, right? So now at a given speed, what do we mean by speed? A rotational speed, say like n over root t naught, non-dimensional form. Okay, so for a given speed it is given, and let's assume it's operating at same inlet temperature condition. Okay, so now I have 2 points. So I think this corresponding to point A and this corresponding to point B, that is missing in this figure. Okay, so what do we have? So this is a maximum pressure ratio for the given speed, and whereas if I go further, it will choke. So it will be maximum mass flow rate for the given engine. Sorry, for the given configuration, right? So now you see isentropic efficiency is directly proportional to the pressure ratio, right? If you look at the form, so we know that it is directly proportional to the pressure ratio. If the pressure ratio is maximum, that means I have a maximum efficiency. So now look at between point A and B. So that means point A should have higher efficiency compared to point B. That is straightforward to see here. And then let us look at the options. What are the options they are given, or what are the statements they are making out of this figure, right? Okay, so they are saying efficiency A is greater than efficiency B, so that is true. So if it is true, then this is not true. In comparison to point B, point A is closer to the surge point. So again, surging is a phenomenon that occurs at high pressure, because high pressure ratios. Why? Because it is a reversal of flow. So that means whenever the pressure ratio reaches to a limit, so after that what happens? The flow starts reversing. So that reversal of flow is going to have a cyclic behavior. So that point we call it as the surging. So that means point A is much closer to the high pressure in the map. So that means it is closer to surge point. So this option is correct. So then in comparison to point A, point B is closer to the choke point. Yes, so because point B is closer to maximum mass flow rate. So when the mass flow rate becomes constant or like chokes, so so that condition we have the point B is closer to maximum mass flow rate condition. So that means option D, or the statement D, is also correct. So A, C, and D are the correct statements. Yes. Okay. So moving on to the next question. In an ideal turbofan engine shown in the figure below, the compressor is driven by a high pressure turbine and the fan is driven by the low pressure turbine. The stations 0, 2, 3, 4, 4.5, and 5 refers to free stream, compressor inlet, compressor outlet, combustor exit, high pressure turbine exit, and low pressure turbine exit respectively. And the subscript T refers to the total condition. Also, they're given tau R is equal to temperature ratio at the inlet, and tau C refers to temperature ratio of the compressor. Tau gamma refers to T at T4 to T0. So that is cycle maximum temperature to the inlet temperature. Okay. So the total temperature ratio of the high pressure turbine, so that is T T4.5 to TT4. So that is temperature ratio of the high pressure turbine they are asking is given by. It is again, so there is a figure that is given to us from the given statement. So what do we have here? So there is a fan that is sitting at the downstream. So that is run by the low pressure turbine. So here we have to see the fan is completely run by low pressure turbine, whereas compressor is completely run by high pressure turbine. Okay, so that means I can match the work for an ideal conditions. So that is work done by low pressure turbine is completely driving the compressor. So I can match those work. And what do we have to find out is the ratio between these two temperatures, total temperature ratio between the across the high pressure turbine. So that we have to find out. Then yeah, so let us start with the balancing work. Okay, so let me just denote all these variables over here, that is T naught and T naught corresponding to station 0, T2 corresponding to station 2, T3 corresponding to, like when I represent with the subscript T, that means total. Okay, so we have T4 and we have T4.5. So this is what we need for this problem, right? Because we are asked to find out these two ratios. Okay, so now if I do the work balance, work done by, did I write it right? No, it is high pressure turbine is running compressor. Okay, so high pressure turbine is running a compressor. So that means Cp times T4 minus T4.5. So that is, let me call this like a T4.5, right? Yeah. So should be equal to Cp times T3 minus T2. Okay, across the turbine. So now, since it's an ideal case, so I can treat Cp to be constant. So neglecting the effect that is coming from combustion. So that means I can write in this fashion. So now also from the given condition, we have T2 is equal to T naught. Why? Because the inlet that we have there, we are treating it to be ideal. So total temperature remains constant. So that means I can write this to be as tau naught, sorry, yeah, tau naught tau r, that is how they are referring, tau r times T naught. Why? Because we know that T naught to T naught ratio is given as tau r. Okay, that's the RAM temperature ratio, let me call like that. Okay, so I can write tau, T naught as tau r times T naught. So I am replacing that one. Also, the compressor pressure ratio can be written as T3 as tau c times T2. So now, since T2 can be written as tau r times T naught, so that becomes tau c tau r times T naught. Great. So similarly, what do we have? Okay. So divide this entire expression by T naught. So to get in this form. Okay. So now what I am going to do here is like, that is T4 divided by my T T4.5 whole divided by T naught, that is equal to TT3 minus TT2 whole divided by T naught. So I am again gonna write in this form, that is tau C tau R T naught minus Tt2, that is tau R times T naught whole divided by T naught. So now you look at, I can write it as T T4 minus I need TT4.5 over TT4. So that means I am keeping this part here. That becomes TT4 divided by T naught minus of all these terms to the other side. So that becomes tau C tau R minus tau R is equal to keeping this to the other side over T naught. Great. So now what is T4 by T naught from the given condition? That is nothing but tau gamma, right? So that's what given in the question. So that is just minus tau C tau R plus tau R. So now here what I can do is I can take tau R common, or just keep like that at this point. Go to the next page. So what we have now is T is equal to tau gamma minus tau R times tau C minus 1. Right? Okay. So now, since we need the ratio of TT4 to TT4.5, so what I'm going to do is like I'm going to multiply and divide it by TT4. If I do that, so now I can write this term as TT4 over T naught. So that is nothing but tau lambda TT times 4.5 over TT of 4. So that is equal to tau gamma minus tau R times tau C minus 1. So now take this tau gamma to the other side. So that gives me T4.5 over TT4. So that is equal to 1 minus tau R over tau gamma, sorry, tau lambda times tau C minus 1. Okay, so this is what we are getting. So let's see about the given options. Tau R by tau gamma, tau C minus 1. Right? So that is option A. That seems correct. So because here we have plus, that's not correct. Plus, minus, that's also not correct. So here minus plus, this also not correct. So option A is correct. Okay, yeah, that's correct. Okay, so now we have question from a rocket propulsion. An ideal rocket has characteristic exhaust velocity of 1200 meters per second, mass flow rate of 75 kgs per second, thrust coefficient of 1.5, and nozzle throat area of 0.025 meter square. The chamber pressure in kilopascal and the specific impulse due to gravity in seconds are respectively. So that's what we need to find out. And they're asking us to take acceleration of gravity as 9.8 meter per second square. Okay, so again, this is a straightforward problem actually. Let us solve. So say like I have a rocket, right? So this is mass flow rate that's going out of the system, and we have given the throat area, so that is 0.025 meter square. The mass flow rate is given as 75 kgs per second, and they're given the characteristic velocity. So how do we define the characteristic velocity? That is P naught AT divided by m dot, right? So where P naught is a chamber pressure, m dot is a mass flow rate, it is throat area. So from this one, we can directly calculate what is P naught. So that is C star m dot over AT. So that gives me, because C star is given to me, that is 1200, mass flow rate is 75, and AT is also given to us. So this should give me the P naught to be around 3600 kilopascal. So that's one part of the solution. So we need to find out a specific impulse. So what is specific impulse? So that is usually defined as thrust per unit weight flow rate of the fuel propellant, right? Mass flow rate times G naught. So now m dot is known to us, G naught is given 9.8 meter per second square, whereas thrust is not given. But to calculate thrust, we have another way, right? So because we are given thrust coefficient, so how do we define the thrust coefficient? That is nothing but thrust divided by P naught times AT. Or I can rearrange this one for thrust. So that is F is equal to CF times P naught AT. So since we already calculated what is P naught, we can directly use here. So everything is known to us. Or you can, if you want, like if you're not sure, like whether I'm getting P naught that is correct or not. So what we can do is like we can rearrange this one. So in what way? So P naught AT can be written as C star times m dot, right? So CF C star dot m dot. So in this way, so you are expressing everything in terms of the given data in the problem, so that like you it's just to make sure like you are not doing any mistakes, especially during gate. Like it's possible if your P naught is wrong, so then you get this is also wrong. So instead you can express again in terms of given numbers, so it will be easy. So if I replace that one, so that becomes CF C star m dot divided by m dot G naught. So m dot get cancels. So I get CF C star by G naught. So that is 1.5 times 1200 meter per second divided by 9.8 meter per second square. So that should give me a specific impulse of 183.67 seconds, because meter per second divided by meter per second square. So I'm left with only second. Okay. So now look at P naught 3600 kilopascal, and this is 183.67 seconds. So that corresponding to option A. So all other options are not correct. Okay. Let's move to the next question. Again, coming from rocket propulsion. Consider a launch vehicle of mass 10 tons being launched vertically. The vehicle has 8 tons of propellant, which burns completely at constant rate over 50 seconds. If the engine specific impulse is 250 seconds and the acceleration due to gravity at sea level is g0, the acceleration experienced by the vehicle at liftoff is okay. Very interesting problem. So let's try to understand what is given. So I have a rocket that needs to be launched, right? So say like this is the mass flow rate of propellant, and overall mass of the rocket is given as 10 tons, so 10 into 10 power 3 kilograms, whereas mass of the propellant is given to be 8 tons, and it burns for 50 seconds. So that means mass flow rate is mp over tb. Okay, so then what else? So I have a rocket that is moving in this direction, so that is say like thrust, right? And gravity is acting in this direction, right? So if gravity is acting in this direction, that means the weight is acting on this direction. So now if I do a simple force balance, so what do we have? The rate of change of momentum, so that is nothing but mass into acceleration, should be equal to the forces acting on the system, so all the external force. So F minus what is this one, that is mass times gravity, right? So that's a simple balance. This is the weight, this is the thrust. So now what is thrust? So thrust can be written as mass flow rate of the propellant times the exhaust velocity, right, for rocket engine. So it's not air breathing, so it's straightforward. Minus m naught g, I'm denoting it as g naught, let me call it as g naught. Okay, so now, so how do you calculate Cj? Exhaust velocity is not given to us. One more variable that is given in the problem, that is specific impulse of this system is 250 seconds. So for in an ideal scenario, so ISP is nothing but thrust divided by mass flow rate of propellant times G naught. So thrust is nothing but mass flow rate of propellant times Cj divided by mass flow rate of propellant by G naught. So if it cancels, so I am left with Cj is equal to ISP, that is specific impulse times gravity vector, magnitude of gravity vector. So I can replace over here m dot p so now the G naught I can take common, times G naught. Straightforward now, right? So m dot p, that we know, that is nothing but mp over burnout time. So if I replace that one, ISP is 250 seconds, mp is 8. So this is nothing but 8 divided by 50 times ISP is 250 minus 10 into 10 power 3, that we cannot forget, so times G naught. So if I put all these conditions, so 5, so it will give me 3 times G, right? So that is nothing but m naught times A. So like, sorry, yeah, so I have to divide it by m naught. is this one, is whole divided by m naught. So if I do that, so whole divided by 10 into 10 power 3. So 10 power 3, 10 power 3 cancels. So I'm left with 3g, right? 3g naught. So that means from the given options, that is option C. Clear? Okay. That was very interesting problem. Okay. Now again we have a question from axial flow machines. The figure below shows a compressor stage with station numbers 1, 2, and 3 as indicated. If P0 I, T0 I, and Ci refers to the average values of total pressure, total temperature, and absolute flow speed, respectively, at the ith station, select the correct options considering the losses. Okay. So first of all, before even looking at the options that we have, so let us try to understand what are the information that we can directly get from here. So I have 1, 2, and 3 corresponding to entry of the rotor, exit of the rotor, and exit of the stator in a compressor stage, right? So now we know that across the compressor's rotor we have energy transfer. So there is a mechanical energy that is being transferred to fluid. So there will be change in energy of the fluid system because of energy transfer or work transfer, we can say. So that means, so let me call P01 and P02 or across the rotor total pressure, so that we know when we add energy to the fluid, so we are going to increase the total pressure of the system because it's assumed to be adiabatic, right? Or in ideal condition it is isentropic. So in any case, so we are going to see P01 that was less initially. Similarly, temperature also. So this happens because we are adding external energy to the system, right? So similarly, if I look at from 2 to 3, that is the stator. So it is here we are not adding or taking any work from the system or heat from the system. It's an adiabatic flow in transformation. So the only condition that we can see here is, since it's steady adiabatic flow scenario, so I can say T03 should be equal to T02 or approximately for an adiabatic condition. Since it's an adiabatic flow, we can still have frictional losses, like it's not reversible. So I can have P03 that is less than or equal to P02. So if it is fully isentropic, so I will be having condition that is equal, but since it's adiabatic, so I can have it is dropped. So these are the information that we can directly get from the given figure. So now let us look at what are the options that we have. So it says that P01 is less than P02. So what did we have? So we arrived that P01 is less than P02. T01 is less than T02. Let me just keep it one side just to compare. So then what do we have? T03 is nearly equal to T02, and P03 is less than P02. So this is the conditions we have, and other than that, what we have? Kinetic energy, so our absolute kinetic energy. So since it is a rotating machine, so what happens? I have a flow that is coming at C1, and as it leaves the rotor, there is C2. So since there is a centripetal acceleration as it rotates, so I have C2 is going to be greater than C1. Whereas in stator, so what we do, we have energy in transformation. So because we are allowing the flow to diffuse, go through a diffuser kind of section, so across the stator, so that means C3 is going to be less than C2. So kinetic energy is converted to static pressure, right? So these are the conditions that we have. Let me write here. C3 is less than C2, whereas C2 is greater than C1. So these are the conditions. So let us look at P01 less than P02, that is correct. P02 greater than P03, that is also correct because total pressure drops across stator. T01 less than T02, that is correct. T02 is approximately equal to T03, that is correct. And C1 is less than C2, yeah, true. Acceleration in rotor and deceleration in stator, so this is true. So the option A seems everything is correct. So other options, if you want to check, you say like this is okay, this is not true always for adiabatic cases, and T01 less than, this is correct, this is correct. So yeah, so this is correct and this is not correct. That's transformation, right? So that means this option is not correct. So similarly, this is correct, this is correct, this is correct, this is not correct for adiabatic assumption, and this is okay. Is it okay? C1 greater than C2? No, not correct. So this is correct. Okay. So this is also not true. Similarly, in this case, which one is not true? P02 less than P03. That's not correct. So for this one, the correct option is A. Okay. Yeah. So then we have this question. Which of the following process or processes is or are involved in the compression of air in an ideal ramjet engine? So in an ideal ramjet engine, what happens? This is my combustion, then it's a nozzle. So we have a supersonic flow that needs to be there, right? So as soon as a supersonic flow encounters a compression corner, so we see an oblique shock, and then there is at the throat we have a normal shock. Also behind that it is subsonic. So we have supersonic part of the diffuser, sonic part of the diffuser. I don't know what's happening. Okay. Okay. This is subsonic part of the diffuser. Okay. So with the ramjet doesn't have any mechanical or moving parts, so this is not correct. So oblique shocks, yes, they do exist, and normal shock, they do exist. Weak normal shocks usually, and then subsonic diffusion. Yes, we have a subsonic diffuser action. So A, C, and D are correct in an ideal ramjet scenario. Okay. So then, okay. So we have a question from turbo machines again. So what do we have? The figure below shows the velocity triangles at the inlet and outlet of the rotor of a low hub to tip ratio axial compressor at the midspan of the blade. Okay. The absolute and relative velocities of the flow are denoted by C and W respectively. The subscripts 1 and 2 refers to the locations before and after the rotor respectively. Fine. So the blade velocity is denoted by U. Select the correct statements for this device. Okay. So what are the information that we have here? So I have blade velocity U is 100 meter per second and axial velocity CA is 80 meter per second. This is the information I have. Also I have, so this length, that is what? That is tangential component of absolute velocity c2. So that is, I can write it as ct2. That is 15 meter per second. So if that is the case, so then here to here it is 60 plus 15, that is total 75. So that is nothing but component of C1. So that is CT1, right? CT1 is equal to 75 meter per second. So these are the information we can directly gather from this figure. Okay. So now, what are the things that is given? What are the statements that we have? Axial velocity is constant across the rotor. Yes, CA is given to be constant, so it's not changed. Same height. The flow coefficient is 0.6. So how do we define the flow coefficient? That is CA by U. So CA is what? 80. U is 100. So that turns out to be 0.8. So this statement is not correct, right? So then they are saying blade loading coefficient is 0.6. So how do you calculate the blade loading coefficient? That is nothing but work done by the compressor to that of the peripheral speed. So W by U square. So W is nothing but a work transfer. So that I can write it as enthalpy change, or in velocity triangles, how I can write? That is U times CT2 minus CT1, right? Divided by U square. So U and U get cancels. So CT2 minus CT1. So we already saw that. That is nothing but 75 minus 15 divided by 100. So that is 0.6. That is correct. These two statements. The last one, if the acoustic velocity at the rotor inlet is given to be 350 meter per second, then the inlet relative Mach number is. So for that, we have to calculate what is a relative Mach number at the inlet. So that is defined as W1 divided by speed of sound at the inlet, right? So this is already given in the problem. First, we have to calculate what is W1. So how do you calculate W1? So W1 is what? I think this is misprinted here. W1. Okay. So W1 is straightforward to calculate. So we know what is U. So first I will calculate what is WT1. So that is nothing but U minus CT1, right? So, and W1 I can write from the Pythagorean triplet. So from the Pythagorean triplet, so this is nothing but.
Can you please write
CT1.
in next page? One request.
So like,
yeah, next page. And second, are all the data, required data available? Because some of the students were claiming some insufficient data in this question. What do you think?
all the required information is actually provided in this problem. So I was just looking at the given velocity triangle. So that seems like, so those velocities looks a SWAT.
Okay.
So
Okay.
you see here C1 and W2, they are not from the same velocity triangle, but like it should be C1 W1 and this should be W2 C2. So
Okay.
I don't know whether it is correctly copied or so like you can just check back when you're putting back here.
Actual paper, you mean? Wait.
Yeah.
Let
So
me
like you can compare between the actual paper
let
and
me
this one.
wait.
Yeah.
Just a moment, because this should not be typo from this. Not should be
Mm.
not from gate part. Wait a minute. Mm.
Mm.
Okay. Where it is this paper? I guess I shared you original paper also day prior.
Yeah. So I have it. I have it. So like I can just open it.
Can you verify? I'll just open and check for myself. Which number? Question number?
I think it's question number 46.
Question number
So
46.
you can see here, right?
Right. Let me check what you're saying with the.
Yeah, in the original paper too, it is misprinted. Yeah. So if you
Yeah,
look.
so that's where a student can claim. Yeah, please go back to.
Yeah. So because C2 has to corresponding to W2 here and W1 and C1. So this is one triangle and this is the other triangle. So that is being misprinted. Yes.
So everyone, please mark this, and those who got confused, or it people can claim for bonus marks, and this will be a 2 marks huge bonus for
Yeah.
those who are on words like they may qualify or not. For them, it can be a big boost. So guys, so what I suggest, I think. Uh, you can write on this what people should write for the contest part, then they can add on. Yeah,
So
we'll do that.
so
We'll ask.
you can just take it as incorrect representation of velocity triangles.
Yeah, perfect.
Okay.
Thank you. Yeah.
So that's what. But like if you want to calculate that one, still you can calculate from the given figure itself. So the other information you can actually see. Um, uh, so
Now
that is
my
like
question is here, can we solve without correcting velocity triangle?
no, with the given information we have to make our own triangle and solve it.
No.
So but
That is not.
yeah.
So
So
means the given representation is wrong, right?
yeah,
That's
yeah. The
where
given
people.
representation is misleading. Yes.
Yeah, that
So
point I can tell. Yeah, please
yeah.
continue.
But yeah, okay. So
So
but
you
we
can
can show that
solve now.
like
Yeah, now
yeah,
you
I
can.
will solve now. Yeah, I will
Yeah,
solve now. So from this triangle, you see, so this part we know that is CT1 or like, sorry. Yeah, so CT1 for this particular problem. And this one is going to be 100 minus that one. So we can always calculate WT1 using the Pythagorean triplet. So that is WT1, CA and W2. So with these three, so I can calculate W1 is nothing but square root of WT1 square plus CA square. So if you put that one, so that will be square root of 100 minus 15. So that will be 85 square plus 80 square. So with that, I can calculate what is W1. So and I know A1 is going to be 350 meter per second. So put this back over here. So you will end up getting 0.333. So this statement is right. Okay. So the only problem here is like the velocity triangle that they are given is misleading because like that information that you have to get is a bit difficult to get because they are swapped the velocities. So that misleads. Okay. Okay. Moving on to the next question. Isobutane is burnt completely in pure oxygen as per the reaction given below. Given that the standard heats of formation in kilocalories per mole of isobutane, carbon dioxide and water vapor are minus 31.489, minus 94.052 and minus 60.150 respectively. The heat of reaction in kilocalories rounded up to 2 decimal places. So they are given reaction. So where isobutane will react with oxygen to form a complete combustion. So form carbon dioxide and water vapors as the byproducts. So now they are asking us to calculate the enthalpy of reaction. So in general, the heat released, or I will call it as enthalpy of reaction, is going to be summation of number of moles of molecules, that whatever we have, number of moles, times enthalpy of formation in products minus summation of enthalpy formation on the reactant side, right? So what are the products that we have? These are the byproducts, right? Carbon dioxide and H2O. So for that, we are already given per mole what is the enthalpy of formation. So that is given to us. So, sorry, this is isobutane. So this corresponding to C4H10. So this corresponding to carbon dioxide, CO2, and this corresponding to H2O. And for oxygen, the enthalpy of formation of oxygen is going to be 0 kilocalories per kilomole. Okay, so with that, so if I substitute back, so I will have enthalpy of formation of reaction is going to be, for the products that I have 4 moles of carbon dioxide, so with the energy content of that one is 94.052 kilocalories per mole. So when I multiply them, so it becomes kilocalories per mole times mole. So that becomes kilocalories. So only left with energy unit, right? So plus I have 5 molecules of water vapor. So that is 5 into minus 60.15. So minus, so for the reaction side, so that is I have 1 mole of isobutane. So it has enthalpy of reaction of minus 31.489. So that was kilocalories per mole multiplied with per mole. So that means mole cancels. I am only left with kilocalories. So that is the unit. Okay. So now it's a straightforward. If you substitute everything back, so we will get minus 645.47. Right? Kilocalories. So this much energy is released. So now what does this negative sign? So this is very important. So you have to put it in the sign along with the number. And what does that negative sign means? It is exothermic reaction. That means heat is being released during the reaction. Okay. Then we have our next question. A furnace of 250 megawatt rating is used to melt and rise the temperature of aluminum from 25 degrees Celsius to 900 degrees Celsius. Aluminum has solid state specific heat, latent heat, and liquid state specific heat of 0.9 kilojoules per kg per Kelvin, 390 kilojoules per kg, and 1.108 kilojoules per kg per Kelvin, respectively. And the furnace has 70% efficiency. The melting point of aluminum is 660 degrees Celsius. So the amount of aluminum that can be processed per hour so in kg. So this problem is very interesting. So it is actually coming from like basics of thermodynamics, not directly from gas turbine propulsion. But let us try to address this problem. Okay, so for this problem, what I try to do here is, so let us first try to model this problem what we have. So I have like a furnace, say, that is at hot, right? So now I have say like aluminum block I am putting that I want to melt it, okay, or process it. So so what are the ways the temperature can change? So one is through a conduction, right? So since it is at very hot, it's a very hot furnace, so as soon as it exchanges heat, so there comes a point like it starts increasing the temperature of an aluminum, right? So it was initially at 25 degrees Celsius, so now I am rising it to 900 degrees Celsius, right? So intermediately I have 660 degrees Celsius where it melts. The moment when it melts, the phase of aluminum has been changed. The when there is a phase of aluminum that is changed, so my total heat transfer per unit mass of the system, say, is going to be heat transfer in solid state plus heat transfer in liquid state plus the latent heat, right? So there is a phase change, so that's why we have to account for the latent heat transfer too. So now it is going to be very straightforward for amount of heat that is being transferred per kg of system. So this is nothing but Cp in solid state times the delta T in solid state plus liquid state Cp times delta T in liquid state plus the latent heat, right? So now in our question Cp is given for both the states, but what is missing? So first we have to calculate the delta T. So delta T is intermediately, it will be in solid state from 25 to 660 degrees Celsius. So this delta T is going to be 660 minus 25. And from 660 to 900, I will have a liquid state. So this is going to be 900 minus 660, right? So it's a final temperature, 900. So since we are taking a difference, so converting it to Kelvin or not, it is not going to change our answer because it's a difference. If I had ratio, you had to convert it to Kelvin before moving forward. But in this case, it is fine. Okay. So now we already have what is latent heat per kg of system. So if you put all the numbers, so this is what 0.9 and this is nothing but 1.108. Yeah, 1.108 into this one, and this is nothing but 390. So everything now is in kilojoules, right? So if I put, so I will end up the heat transfer, it's going to be 1227.42 kilojoules per kg. It is unit mass system at this point. So now what is the energy balance that we have to do? This is the heat being transferred. So to do that, how much of energy that you have actually supplied, right? So that is coming from furnace. So energy that's been transferred by this furnace, because it has a capacity of 250 megawatt, 10 to the power of 6 joules per second, right? And it is only efficient like 70% efficient. So that means multiplied with efficiency, that is 0.7. So this is the energy that is being supplied to do this much of heat transfer. So now I am trying to do the energy balance. So that means the energy balance says me that is per unit mass system. So I have to include now mass of the aluminum that has undergone this much of heat transfer, right? So if I include that one, so I can write mass to be equal to energy per heat transfer. So that is nothing but 0.7 into 250 into 10 to the power of 6 divided by whatever we got, 1227.42. So now look at into 10 power 3, that is in joules per kg. This is in joules per second. So joules get cancels. And what I'm left with? I'm left with kg, right? Yeah. So I'm left with kg per second. Whatever I'm going to get, it is in kg per second. So, but what I have to do, I have to calculate for 1 hour, right? So whatever you are going to get from this, so it is in kgs per second. So if I multiply that one with 3600 seconds, so I can get rid of seconds, but I get in the form of just mass. So like just multiply this entire thing with 3600 seconds, that is per hour, right? So we have 513,271.74 kg per hour. Okay, so rounding off to 1 decimal places, that's 513,271.7 I can write kg per hour. So this much aluminum we can process. So what was the answer given? Yeah, the range is between 270 to 272. So we are getting 271.7. So within the range. Okay. This was again very interesting problem coming from pure fundamental thermodynamics. Okay. So now we have a question number 61. That is coming from a radial compressor, right? Or yeah. So we have a centrifugal compressor has a constant width radial diffuser. The diameters at the diffuser inlet and outlet are 0.2 meter and 0.3 meter respectively. The flow at the diffuser inlet and the outlet is assumed to be steady and uniform. The average velocity at the diffuser inlet and outlet are given in vectorial form, but it is radial velocity 60 meter per second and tangential velocity 75 meter per second at the inlet, and at the outlet you have unknown radial velocity and tangential velocity is 50 meter per second, okay, respectively. If the flow through the diffuser is treated as steady and incompressible, the value of u, so we have to calculate this radial velocity at the exit, rounded off to nearest integer. Okay, so now let us try to solve for the problem. First we have to understand the problem. So I have a radial or the centrifugal compressor. So I'm just drawing one part of this one. So now you see I have a diffuser at the exit plane, right? So this is a radial diffuser. So what is given in the problem is the diameter at the inlet and diameter at the outlet of this diffuser. So this is my diffuser. So that means like I have R1 and R2 inlet and outlet diameter, and we can treat it as incompressible. That's what they are saying inside the diffuser, because we are out of compressor now. So sorry, impeller now. So I will treat density to be constant across the diffuser So simple continuity tells us mass flow rate is constant. So if mass flow rate is constant, so what does it mean? Rho CR1. So say like this is rotating in this direction. So if I make a 2D diagram for this one from the other plane. So this is CR and right, this is CR. This is going to be C theta, right? Tangential direction. Similarly, I have CR C theta, right? So this is CR1 at the entrance, CR2 at the exit. 1 C theta 2. So and this one is given to us, like the information is given in terms of velocity vectors. So rho CR1 A1 should be equal to rho CR2 A2. So now rho and rho get cancelled. And how do we calculate area? So like let us try to visualize it, right? So this is my part of the impeller, say, right? So this is going to be my width B. And in the problem it is said the width is constant. So from here the diffuser will start at the exit plane. So from here we have a diffuser that's going to be start. So this width is fixed in. We have to look from the isometric view to understand how that looks, right? So these are all impeller blades. So this is my width through which the flow is going out, right? Or in the other words, right? So this is how my diffuser would look like. So this width and this width is going to be constant. So at this point or at this point, that is constant. So it's only varying radially, right? So that means my diffuser would look like this, but the width that I am talking about is constant. So this width. Okay. So that is given in the problem. So constant width. So which means area can be written as pi d times b, right? That is a diameter, circumference times the width will give me the area through which the flow is going. So that means that is my area. So if I use that one, CR1 pi d1 b is equal to CR2 pi d2 b. So this and this can be cancelled. So I'm left with CR1b is equal to CR2b. So now it is straightforward. So all we have to calculate is what is CR2. 1 second. CR1 d1 is equal to CR2 d2, right? B is constant. Yeah. So now CR2 is going to be d1 by d2 times CR1, right? So now you put everything that you have. D1 is 0.2 divided by 0.3 multiplied with CR1. CR1 is given in velocity triangle, sorry, velocity vector. So that is 60 meter per second. So if you use that one, so that will be user. So that will be 40 meter per second, right? So 39 to 40, yeah. So we are in the range. So we get 40 meter per second. So like we get exactly 40. So it is nearest integer is 40 only. The next question, we have a gas mixture at a presence of 800 kilopascal and a pressure of 800 kilopascal and a density of 5 kilograms per meter cube enters a turbine stage. The temperature of the gas at the nozzle exit and the stage exit are 790 Kelvin and 750 Kelvin respectively. Assume the specific heats are constant for the gas mixture in the range of temperatures considered. The specific heat at constant pressure is 0.72 kilojoules per kg Kelvin, and the ratio of specific heats is 1.33. The value of the degree of reaction of the turbine stage, rounded off to 2 decimal places. It is again a straightforward problem in some sense. So what do we have? So we have a turbine stage. So let me call it as station 1, station 2, station 3. Right? So it is entering with a pressure of 800 Kelvin and temperature, density of 5 kilograms per meter cube. Right? So then at station 2, I have 790 Kelvin, and at station 3, I have temperature of 750 Kelvin. So all they are asking is the degree of reaction. Degree of reaction for the given condition. So we can define it as enthalpy change in the rotor to that of enthalpy change in the stage. Right? So for a given gas, Cp is constant, so I can write it as T2 minus T3 divided by T1 minus T3, right? So this is a change in rotor and this is a change in stage. Sorry, so stator, so or the nozzle. So nozzle plus rotor is stage. So that means T2 minus T3, so that is 790 minus 750 divided by, so how do we calculate T1? So T1 from perfect gas, P is equal to rho RT, or T can be written as P over rho R, right? So that is P1 over rho 1 times R minus T3. So P1 is known, rho 1 is known, but R is not known. So how do we calculate R? R can be written as gamma by gamma minus 1 times Cp, right? Cp minus Cv is equal to R. So from there we can express this way. Sorry, it's the other way around. Gamma minus 1 divided by gamma times Cp. Yeah. So gamma is 1.33 given in the problem. Cp is again given in the problem. Cp is given 720 joules per kg per Kelvin. So if you put that one, so you should be able to get R, that is equal to 178.65. joules per kg per Kelvin. So that is R. So substitute back over here. So you should be able to get T1. So from here, so if you put that, 790 minus 750 is 40 divided by, this is 895.62 minus T3. T3 is 750. So that is my degree of reaction. So that turns out to be approximately 0.27. Like I am rounding up to, so 2 decimal places is coming to be 275 equal to or approximately 0.28. Rounding up to 2 decimal place. Yeah, so we're in the range. Okay. Yeah, so that's about our questions from propulsion. So This paper was relatively challenging compared to other papers that we had in recent years, but it was an interesting paper. Okay. So that ends our discussion on this year's paper. Thank you, everyone.